And it is streaming. All right, so does anyone need access to the live stream? Okay, so let me publish that. Okay. Yeah, I will try to streamline this a little bit more later in the semester, because in both of my classes, having the URL to the live stream is actually helpful to some people. So right now it's all done manually, which is a little bit of a hassle, but it can be done. Copy link location, and go back to I got too many tabs open. Hmm? No such thing. Yeah, I have a little tool to help me manage all the tabs. It's called a tree style tab. So you can see how the tabs are actually listed on the other side. So I can actually see the title, or at least a little bit of each title on the tab. But it takes away the actual screen area. So that's why I usually turn it off unless I want it, unless I have the full screen. But you don't. This is not the full screen.
Does it only open on one side?
I have not looked into it, so I'm not sure whether you can open it on the other side. I'm assuming it might be flexible enough to open on the other side. But it's a great tool. Okay, if you're running a 4K monitor, this is great.
That's why I was asking.
Yeah, I have a 4K at home, a 4K monitor at home, and that works really well when I'm home. But here we have 1280 by 720, so it doesn't work well like that. Sorry? Huh? Sorry?
Which one's 1280 by 720?
The projector. The projector is only 1280 by 720. All right, so mic is on. All right, so I've got one last thing to do, which is to get to announcement, make a new one. Okay. And we say YouTube link. Paste it here. Save. There we go. And there we have it. So now we can go back there. I have a student who needs a captioner in one of my other class. It sounds really strange. And the captioner is not even in the class, so they're doing it remotely. And the captioner said, told the student, because the student has a kind of specialized tablet that has the software for the captioner to hear what is going on. So instead of doing that, the captioner is using my stream, and the captioner said my stream has a much better audio quality compared to what is captured by the mic of the tablet that the student has. And the student is already sitting in the front row. So that kind of works out really kind of cool. Do you have a question?
No, just want to update this stuff.
Hmm?
This flyer
Uh-huh.
from last semester, I just want to update it and put a new one there.
Okay, can you do it quickly?
Yes.
Yeah, okay.
Thank you.
So that gives me a little bit of time to get to the note that we'll be using today, which is basic quantifiers. I'm hoping most of you has a chance to read a little bit of this before class, because that kind of really helps. And if you have any questions while you're reading it, you probably want to ask those questions if I cannot clarify the concepts in the lecture. And it still sounds really kind of strange because I'm just kind of decreasing the volume, step by step until it sounds normal. All right. So, yeah.
Can we go over the ungraded assignment?
The ungraded assignment, yes. So let me go back there, go to announcements. I know I forget something. I always forget something. Like today, I forgot to bring my row sheet. On Monday, I brought the row sheet, but then I forgot to pass it along. All right, so let's take a look at all of these interesting questions. The first one, what do you think is the answer to this question? So I can just say, okay, it's the cardinality of, right, a set. What is in that set? Another set. What is in that set? It is another set. What is in that set? Nothing. Okay, so when you look at the actual value that this expression is going to return, what is it? 1. Very good. Okay, because the one thing that we are counting is this. I just want to highlight. Oh, okay, it won't let me do it. Okay, so the one thing that we are counting is this. It is the set that contains the empty set. That is the one thing in the set from which we want to compute the cardinality. Are we good so far? Okay. Shall we move on? Okay. Next question. So once again, we are looking at the cardinality of something. So what is the cardinality of the set that is, represented by the outermost curly braces? 2. Very good. Excellent. What about the third question? The third question is using the in or is an element of operator. You can call it either way. So that's a Boolean. Okay, it returns a Boolean. It's either true or false. So what is the answer in this case?
True.
It is true. Okay, very good. What about the next one? True again. Okay, but that's because I make the set kind of tricky, because A, B are individual elements of the set, but the set that contains A, B is by itself an element as well. So it's a little bit tricky. Okay, so now we get to this question here. Is that true or not? It is also true because, well, okay, first of all, it has to be a subset first, okay? But being a subset is not enough to be a proper subset. In order to be a proper subset, AB has to miss at least one of the elements of the other set. So the element is missing is the set AB itself on the other side. Okay. All right, moving on to the next one. This one is a Cartesian product. Okay, so with this one, I'm going to use Notepad because it's easier or faster for me to type it than to just kind of spell out the answer. So let's go to mousepad. All right. So one thing we know about the elements, okay, every single element of a Cartesian product is going to be a 2-tuple. We know that just because it's a Cartesian product. Okay, so we open with a curly brace, and the order is not important. Remember, in a set, ordering is not important. So we use an open parenthesis to start a 2-tuple. But if I want to do it kind of systematically, I can now pick out the first element of the first set as it is listed here, pick out the first element of the second set, and that becomes the first tuple. Okay. Now you can do it in any order you want, okay? But I just want to do it kind of systematically so I don't miss anything. This is the second element, and then the third one is the set that has an empty set, and then A by itself, and then the last one is going to be the set of an empty set as the first item of the 2-tuple, and then the set that only contains A as the second item of the 2-tuple. And we have 4 2-tuples because there are 2 elements from the first set, or the one from the left-hand side of the Cartesian product, and also 2 items from the set on the right-hand side of the Cartesian product. So 2 by 2 gives us 4. Are we good so far with this question? Now the elements look kind of awkward and strange and whatnot. It doesn't really matter, okay? We just pick out one element from this, element from that, make a 2-tuple out of it, throw it into the Cartesian product, and then do the same thing again with the other elements. Okay. All right, so this is the solution of the first Cartesian product, the only Cartesian product question. So now we move on to the next one, which is testing whether you know what is a union. So what do you think is the union between these 2 sets? It's going to be hard to say it, but go ahead, try. Yeah.
The set that contains the set AB and the set ABC.
That is correct. You spelled it out correctly. So the union of the third question from the bottom is a set, but in the set we have one element which by itself is a set of AB, and then the second element is the set of ABC. Are we doing okay so far? All right, cool. And here is the second last question. The second last question is an intersection question. The first set, or the set to the left-hand side of the intersection operator, has two elements. Okay, AB as a set being the first element, the set ABCD being the second element of the set to the left-hand side of the intersection. And then on the right-hand side, we have ABC as a set. So what is the intersection between those two sets? In other words, which elements are common to both sets? What do you think? There's absolutely nothing in common, right? So the intersection is an empty set. Are we good so far? Okay. And then the last question is also a Cartesian product question, but it's a very easy one. Because the Cartesian product basically says, okay, I'm made out of a whole bunch of two tuples. Okay? But in each two tuple, the first item comes from the set to the left-hand side, the second item comes from the set on the right-hand side of the Cartesian product operator, right? Then you look at the one on the left-hand side and say, but you're an empty set. Well, if that is an empty set, then you have nothing in the Cartesian product. So the Cartesian product is also an empty set. Are we good so far? Yes?
So it's
Okay.
something akin to multiplication without actually being multiplication.
It is multiplication. You can consider this as 0 times something, right? 0 times whatever is always 0.
Right.
So you can look at it that way.
Okay.
Because we're trying to pair up things, right? If one set is not contributing anything at all, then we cannot pair. There's no such thing as a pair in the result because one set has nothing in it. You cannot create a single two tuple where the first item comes from the first set because the first set is empty.
Okay.
So is that okay? So how, yeah, go ahead.
Can you just explain the union operator one more time?
The union operator, this one?
Yes.
Yeah, so the union operator is, so any element in the union can be found in on at least one of the two sides of the union operator. That's basically how a union is defined. So in this case, the union is going to be this particular set because AB as a set is found on the left-hand side or the set to the left-hand side, and then the set of ABC is found as an element of the set to the right-hand side of the union operator. Okay. So are there any questions about these kind of brain teasers? No questions? Okay. If you guys want to ask what if questions, that's perfectly okay. Okay. So if you say, but what if we do this and this and this to this particular expression, what will be the answer in that case? Okay. Those are really great exercises because not only are you answering the question that I'm asking, you are actively making new questions for yourself. So if you have those new questions that you're generating by yourself and you're not quite sure what the answer is, ask me about it. Yes?
So for the last one, if the first set had 3 elements and one of those elements was also an empty set, does it still return any tuples out of that?
Okay, so let's make it happen, right? So you are basically saying that we want the first set or the set to the left-hand side to have 3 elements.
Right.
Of which one is an empty set, right? So let's say do you want to reuse AB or just or 1 2? 1 2. Okay, so we have 1 2 an empty set that is to the left hand side. then we have the right-hand side being the same as ABC, right? Okay. So we know the end result of this Cartesian product has 9 elements because there are 3 from the first, 3 from the second. 3 by 3 is 9, okay? So now the question is, what are those 9 individual elements? So we also know the result is a set, okay? So we already know that, okay, we need the curly braces. In a set, the ordering is not important, but I will do it systematically. So I'm going to fix the first element to fix the first item of the 2 tuple to the first element listed here, just so that I go through this systematically. So it will match up with A initially, for the first one, match up with B, and then it will match up with C. Then I take the second element of the first set, just so that I can do this systematically. Okay, so we have 2A, 2B, and 2C. And we're not done yet because there are 3 elements in the first set. The third element, at least according to the ordering of how it's listed, which is insignificant, is the empty set. But the empty set is acting as an element of the first set or the set to the left-hand side of the operator. So we just treat the empty set as if it is just a thing, okay? So now the next 2 tuples will have the first item being an empty set, and then the second item goes through A, B, and C, just like earlier. So I'm going to enumerate all of these so that you have the complete answer to this question. Okay, 1 extra comma here, and that. Yep.
So the first set was an empty set, an element of a set that would give you a 10 by 9, right? An empty set in the first.
You mean if this one is an empty set?
No, in your original question, if there's 2 more curly braces.
You mean if
Yes.
here,
It was an empty set inside it.
if it has an empty set inside, then we'll have 3 elements in the Cartesian product,
Yeah.
right? So every single element in that case will have the first item of the 2 tuple being the empty set, and then the second item of the 2 tuples going through A, B, and C. Yep.
Is this something we should expect to see on an exam, or is it just practice?
Oh, this is relatively easy compared to the questions you will see in the exam. Yep, go ahead. Back there first and then back to you. Yep.
Since there's just nothing in, like in the original question, since there's just nothing in it, like not even an empty set, it's just the answer is an empty set. Like
For which question?
the original, the last one.
For the last one,
original one.
the answer is the empty set.
Yeah, just because there's nothing. If it had an empty set inside that,
Mhm.
that would be something. But since it doesn't have even that, it's
Correct.
just an empty
Yes.
set.
Yep. And back to you.
So just to clarify for the subset and the proper subset question,
Mhm.
if you were to delete element A and element B from the right-hand side on both of them, the
Mhm.
first one would still be true and the second one would be false, right?
So we take out B from both,
Oh,
right?
the right-hand side.
Or from the other side,
The element
if
A.
we take out B, the actual value B, right, from the set itself, not from here,
Not from there.
from here, right?
A and B.
Both A and B?
Yeah.
If you take out both A and B, then the answer would be false to both of these. Yeah. Yeah. Because if you take out AB or just A, okay, or just B, then AB as a set is no longer a subset of the other one because it would have missed one of these two. Remember, in order for the set on the left-hand side to be a subset of the set to the right-hand side, every element of the one to the left-hand side has to be found on the set to the right-hand side.
Well, maybe I was thinking if you deleted the A, B, and the...
If you delete this,
Yeah.
it will be okay. If you delete AB as a set from the right-hand side, then the subset will still hold, but the proper subset would not, because AB is not a proper subset of itself. Okay, very good. I like these kind of on-the-fly question generation. Yep.
Would it be for the 4th question, would it be correct to say the set of the set AB is a subset of that set?
the fourth question here. So the reason why AB is a subset of this side has nothing to do with this guy.
Right.
It only has to do with AB individually are elements of the second set.
Correct. But would it be correct to say that the set of the set AB is a subset?
Yes.
Okay.
Yes. So you guys can think of even more tricky questions than I do. That's a good sign. That is a good sign. All right. Any other questions about the ungraded assignment? No questions? All right, cool. So now we can move on to the quantifiers, okay? So quantifiers is a very fancy term. You use it almost every single day. Okay, I take it back. You use it almost every single hour. Not every single day, but every hour. Because I just used it twice already in the previous sentence. Every, okay? That's a quantifier, okay? So in real life, quantifiers are all, okay? None, some, okay? Those are all quantifiers, at least one, okay? Those are all quantifiers that we use almost on a daily basis, okay? So when do you use all, okay? Hmm?
The entire amount.
The entire, without exception, right? Okay? So somebody can say, I failed all of tax classes. Okay? That is a quantifier, okay? As opposed to that person saying, I failed at least one of tax classes. So those two sentences are very different, okay? Versus a person saying, I failed none of tax classes. Now, they are related because if you can say, I did not fail at least one of tax classes, it is the same as saying I failed none of tax classes. Does that make sense? Yes? And that's all without using the operators that we're going to introduce. We are just talking about how we use all, every, all, and none, and also negation in real life. Are we good so far? Yes? So this is not a new concept, okay? In other words, I just want to ease your mind to let you know that you're not learning something that is completely conceptually new to you. It's just that we are now looking at these using specific symbols in order to specify other things that we need to specify in this class. But conceptually speaking, we already understand these concepts. So the first thing we need to go through is to talk about what is a predicate, okay? So px here is what we know as a predicate. Now, what exactly does it define? I don't really care, okay? The only thing I know is x is serving as a parameter and p returns a Boolean, okay? You give me something, x, and I'll tell you whether p of x is true or false. So that's what p is here for. Okay, it is just some kind of big, huge Boolean operation, and in the end, it just tells you either true or false. Okay, for that specific value x. Is that okay? All right. So let's take a look at this notation here. Okay, this is the for all notation. Now, the easy way to differentiate between for all versus there exist is for all looks like an A. For all, except it's upside down. There exist looks like an E, except it is flipped horizontally. So that's a quick and easy way to associate which one is for all and which one is there exists. Are we doing okay? All right. So this one is saying by itself, okay? This expression, the one that is highlighted right now, by itself is a Boolean expression. It can either be true or false, okay? So this is saying for all x, p of x is true. That's basically what it's saying. But what if I can find an x to make p of x false? Then this whole thing, for all x, px is true, that whole thing is false. Are we doing okay with that concept? In other words, this is not an assertion that p of x is true for every x. It is merely asking, is that actually true or not? Are we good so far? Okay, so the for all symbol, the quantifier, is a part of an expression that can return true or false. It does not assert something, it's not defining something. Okay, so in English, it is saying for all x in the entire universe, p of x is true. That statement itself can be true or false. Are we good so far? Okay, I'm just repeating myself because this is just what is written. Okay. Now, what about the other one? Well, the other one is really just replacing for all with there exists. So this one here, the one that I'm highlighting right now, is saying there exists at least one thing in this entire universe such that p of x is true. Are we doing okay so far with both of those? Now remember, without any further qualifications, this x applies to everything in the universe, in existence. Okay? So that includes humans, cars, molecules in the air, planets, suns, stars, galaxies, and so on and so forth. Okay? So it's difficult to find something that is universally true for everything in the universe, right? So how do we deal with that problem? Okay, we'll take a look later. But we'll pause here and I'll see if there are any questions about the concept of these quantifiers. Okay? Now the name quantifiers comes from quantity, right? Which is the amount of. So quantifiers is basically just saying, okay, I understand that you're trying to say something is either true or false, but are you saying that everything applies, this applies to everything, or it applies to just one thing? Okay, that's basically what a quantifier is for, is to specify, are you talking about everything or are you just talking about one individual? Okay, so I'll give you an example. All CIS professors suck. That's a universal quantifier. That's for all. Okay? Or at least one CIS professor sucks. Then you're saying, well, if you go take a class in CIS, you might encounter that one professor, at least one professor who sucks. But there may be other professors who do not suck. Okay? As opposed to negation, okay? It is not the case that there exists a professor in CIS who sucks. That is really saying the same thing as we are all good. All CIS professors are good. None of us suck. Is that okay? Okay. So now we look at, so I have just illustrated examples of how negation can be applied on top of quantifiers. Okay? So we'll go through a few examples and figure out, what does it mean? Okay? So we'll focus on this one first. Let me put the cursor on that so we can see which one we are focusing on. All right, we'll focus on this one, which is basically saying it is not the case that there exists at least one thing in this entire universe such that p of x is true. Exactly what is that saying? As it turns out, it's saying the same thing as the other expression. So remember this one? It is saying it is not the case that exists at least one thing in this entire universe such that p of x is true. The second one, which is equivalent to the first one, is saying everything in this entire universe, for everything in this entire universe, p of x is not true. So intuitively, do you see how these two statements are equivalent? Yes or no? Okay, very good. Okay, so it should make sense to you, because the symbols are new to us, but what it translates to is something that we kind of know already. Are we okay with this and move on, or do you want to kind of talk about this a little bit more? Okay, looks like everybody's ready to move on. So you can see how we are moving the negation to the inside. Okay? But in doing so, you have to change the quantifier from there exists to for all. So that is the trick. Okay? So you will see in this class that there are other tricks of moving negation into the inside of something. Okay? This is just one of the examples of moving the negation, logical negation, into the inside of something. So the second one we want to focus on is this one here. Okay? So literally what it is really saying is it is not the case that everything in the universe, for everything in the universe, P of x is true. Okay, that's literally what it's saying. Okay, it is negating that for all x, P of x is true. So what is the meaning? Well, you can move the negation again. So you can see how we move the negation to the inside, and then we are changing the quantifier to the other one. So the second way to say exactly the same thing is to say there is at least one thing in this entire universe such that P of x is false. So intuitively, do you see the connection? See how those two statements are the same? Yes? No? Kind of makes sense? Okay, very good. So the other way we can say that is to say that this particular expression is always true. What is it saying? It is saying that it is not the case that for every x in the entire universe, P of x is true. This thing is true if and only if there exists at least one thing in this entire universe such that P of x is false. But I'm just saying that these two expressions are equivalent. So that's why if and only if, which is the double-sided arrow with two bars, is also known as is equivalent to. So there are two ways to name this operator here. You can call this if and only if. You can also call this is equivalent to. Are we doing okay so far with the discussion up to this point? Yes?
I just have one more clarification.
Mm-hmm.
So whatever's in the parentheses with the predicate, we're saying that that needs to be true. So there exists x such that not P of x, and the goal would be to prove that.
There's no goal. There are no proofs at this point. I'm just introducing operators that we'll use later on. Okay. So in this case, I'm introducing quantifiers and how quantifiers can interact with negation. So this thing by itself can be true, can be false. Okay. But in order for this expression to be true, then you have to find me at least one thing in the entire universe such that P of x is false. If you can do that, then we can say this expression is true. But if you cannot find me at least one thing such that P of x is false, then this entire expression is false. Is that good? Yeah. All right. So we are really just playing with symbols. Okay, we are just basically saying, okay, we understand these concepts already. We know how to say it in English or some other natural languages. But what does it look like in mathematical symbols? Okay, that's basically what we are doing at this point. Okay, are we good so far? Yes, go ahead.
So could we say that that first statement says nothing is true, which implies that at least something is false?
Okay, so the first one, which is the one that is blinking right now, is saying it is not the case that everything for every x, P of x is true. That's what it's saying. Okay? It is not the case that for every x in the entire universe, P of x is true. But that kind of intuitively is saying that there exists at least one thing where P of x is false. Yeah, so that's basically the bottom line of the equivalency between these two expressions. They're expressed differently. So you might ask, why do we need to know the alternative or equivalent expression? The whole idea is, a lot of times, we want to move negations all the way into the inside. And this allows us to take the negation, which originally applies to the for all quantifier, so that it now applies to the predicate. Is that okay? All right. If you have any questions, we can always kind of go back to an earlier concept, so that's okay, don't worry. And now we're moving on to filtering. So a lot of times, we don't really want to look at everything in the entire universe, okay? We might want to just look at integers. Sometimes we only want to look at non-negative integers. Other times we want to look at just even numbers, okay? So how do I filter out all the other stuff that is of no consequence to me? Okay? So the idea is we want to filter by saying, this is the mechanism of the filter, okay? So let's just say that, I will give you an example. So let's just say that we want to check out, whether CIS professors at ARC sucks or not, okay? We good? So we don't want to, I don't want to know whether, professors at Sac City, suck or not. We don't care about, CRC or, FLC. We just want to focus on this campus, okay? So how do we do it? So P of X or P of E in this case is, does E suck, right? And then this E here, okay, this lowercase e, after the for all, that applies to everything in existence, okay? So we are not only talking about professors, we are also talking about presidents, vice presidents, normal people, your pet, the parasite that lives on your pet, the fungus that lives on the parasite on your pet, the virus that is invading the bacteria that is living on the parasite on your pet, everything under the sun. Well, shouldn't say under the sun because there are a lot of things not under the sun, but this E applies to everything. It binds to everything that is in existence, okay? So how do we say, well, if it is not a professor at ARC, I don't care. So X is a set, okay? X is the set of all professors at ARC. Okay, so are we good so far? Do we see? So the only thing you have to remember right now mentally is X is representing all professors at ARC. Are we good so far? Now remember, this E is can bind to anything in existence. Okay, so what if E is binding currently to a particular virus that is invading a bacteria that is living on a parasite that is on your pet? Okay, then you say, okay, this E is an individual virus. The first question you ask is that virus a professor at ARC? I certainly hope not, right? So that means E in X is going to be false. Okay, so what do we know about implications? If the first part of an implication is false, what happens to the value of the implication itself? Is true. Okay, so if E is bound to a virus, then this expression in parentheses is actually true. Do you see how this is doing the filtering? Because anything that is not a professor at ARC will automatically make this portion of the expression true. What can make it false then? Well, the only thing that can make this part of the expression false is E is in fact a professor at ARC, but P of E is false. That is how you make this part false. Yep?
Wouldn't E be limited to the valid parameters in the predicate anyway? I mean, if your function only takes integers, you're not going to put like a molecule into a function.
That is true, but this is how but you can filter even further because, let's say you're looking at even numbers, right? Well, odd numbers are numbers too, so whatever you can do with even numbers can also be done to odd numbers. So this will help you filter out the odd numbers. And by the way, a virus can suck too, just like a professor.
Set was all humans, then
Yes. The implication, E in X is also doing what we know as a guard condition in C and C++. Okay, now I hope you guys still remember that when you have a conjunction, a logical AND as an expression in C or C++, it uses what we call short-circuited evaluation. Do you guys understand what I'm talking about? I hope so, okay? So that's a filtering mechanism, because if the first condition or the condition to the left-hand side of the conjunction is false, it doesn't bother to evaluate the expression on the right-hand side. So you can now say x does not equal to 0 and y divided by x is blah, 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 blah. Because by the time you get to y divided by x, you already know that x is non-zero. You will never get the division by 0 problem. So this is basically serving the same purpose. It is a filter, it is a guard condition. And basically saying, hey, if E is not in the set X, we'll just automatically make the condition true because it doesn't really matter to me. It is of no importance to me. Is that okay? Okay, cool. Now, because this is inside the for all, so that means if I can find at least one thing such that that thing is in X, but P of X is false, that makes the entire for all expression false. Because I just found one thing such that P of X is false, and it is also in X. Is that okay? All right. So this filtering mechanism is very useful. You can also reverse it, okay? So you can use. So this part is really just using an example to illustrate the logic of how you can apply this. And this is the short form. So the last part here is these two expressions are exactly the same. So let me just kind of spell out each one. So instead of just P of E, we have the negation of P of E. So that's a kind of minor thing. But the idea of this between these two expressions is instead of using E in X as a part of an implication, we move it out to say that for all E in X, the following is true. So it's a shorthand that makes more sense to some people. Are we doing okay so far? So we're basically doing the filtering or the guarding, right next to the for all quantifier, instead of expressing E in X as a separate condition inside the parentheses. So it's you can look at it as a shorthand. Are we okay with the symbols and the expressions? Yes? Okay. All right. So if that is okay, we're going to go back to the class, and then we're going to move on. We will move back to set theory, but this time we'll use quantifiers to define some of those operators. So we will first deal with equality. So section 3 talks about equality. How do we know, two items are the same? Okay. So we are given two items. Okay. Each item can be just an item, but it can also be a set. Okay. So we basically say that if we know that X and Y are both sets, then we use this to say X is equivalent to Y if and only if for everything in X, E is also in Y, and for everything in Y, E is also in X. So now you have to remember local scoping in C++ or most modern programming languages. This E has a scope of here. So this E has nothing to do with that E, because each E is only, so after the quantifier, that symbol only has meaning in this particular expression. It has no meaning other than outside of that expression. Are we doing okay so far? So we have two local variables E, but they're in two different scopes. So they are entirely independent to each other. So are we good so far? All right. And you can also say it in this particular way. You can basically say X is the same as Y if and only if for everything in E, for every E E is in X if and only if E is in Y. So that basically says exactly the same thing as the original. Does that make sense, or do you guys want to talk about it? Yes?
So when you have the statement directly after, like if for all E in X, E is in Y,
Uh-huh.
when the statement in the parentheses is implied to be true, there's nothing that explicitly states that, but the implication is that this is true, and then you're evaluating that as a statement saying, is it true, right?
You mean this part here, right?
Yeah, but specifically like the E is in Y of that. So the last portion of it, it's always assumed that you're evaluating it as if that is true, right?
Right. So what this portion, let me highlight it before I talk about it. Okay, so this is the sub-expression that we are talking about. So what this is saying is, I'm not interested in anything other than elements of X. Okay, that's what the first part is saying. Is that okay? So by the time we get to E in Y, we already know that E is in X. So E in Y is Boolean, gives me either true or false value, right? So when you combine this true or false value with a quantifier, it means in order for the for all expression to be true, everything in X better be in Y as well. That's what it's saying. Yep. So the change here is we are now using quantifiers to basically define the same thing that we have defined earlier when we talk about set theory, except this time, we are using quantifiers. Are we good so far? Yes? Okay. And I think one mic, oh, no, it's still here. I thought it just died. Okay, so we want to look at set description. Okay, so remember that thing, we have an E, we have a set E, and instead of listing everything out, I want to just say, well, if it meets this requirement, it is in the set. Remember that? Okay, so this notation over here is basically saying the same thing as this notation here. Now let's take a look at this one, the second one. I'm going to highlight it so we can talk about it. Okay, so we'll take a look at this one. So this one is saying for everything under the sun, okay, in the entire universe in existence, if X is in E, if and only if P of X is true. Now, in this case, it is very important to remember this is if and only if, and not just if. Okay, it doesn't just go in one direction, it has to go in both directions. Because what this is saying is if X is not in E, P of X better be false. Vice versa. If P of X is false, X in E better be false too. And then, if X is in E, P of X should be true. If P of X is true, X should be in E. So it's implying, it's basically telling us all those four individual things are true, depending on which X we are talking about. Is that okay? Does everybody see how the notation here is really saying the same thing as this notation here? Yes?
Can that also just be written as for all X in E P of X? Since
No, it is not exactly the same thing. Because that notation, okay, let me go back to the previous slide because that helps. That will help. So that's a very good question. It's a very, very good question. So I think it's under here. Nope, that's the same. Where did it open? Yep, there we go. Okay. So we're talking about filtering.
oh, that one's implied.
Yeah, that's only implies. Yep. We don't want implies, we want if and only if. Yep. Okay, let me put this side by side so that people can see what I'm talking about. Okay, I need to take this out on its own. Okay, there we go. And we look at this one here, and then we look at this one here. Okay, I'm not sure how I can highlight two things at the same time, probably cannot. So I will just kind of point it out here. We are comparing this, which is equivalent to this notation, to this, which is equivalent to the notation that we worked with. Where is it? Where the E in X is on the outside. It looks like this, okay, but they're not the same because one has an implication and the other one has an if and only if. The difference is if I use just this notation here, that means if something is in X, we know for sure P of E is true. Is that okay? But there may be other things in where P of E is true and it is not an element of X. That is allowed to happen when you only have implication. When you have if and only if, or is equivalent to, that cannot happen. Everything that makes P true has to be in E, and everything that makes P of X false cannot be in X. So it's a much stricter type of limitation compared to implication. Is that okay?
Yeah.
That was a good question because these two can be, they're close. Okay, so it is important to differentiate between those two. So before I close the window to the right-hand side, do we have any additional questions about the differentiation between the implication and versus the if and only if? We're good? All right. All right, so let's talk about the empty set. So how do we know that S is an empty set? Well, if S is empty, then this expression should be true. Because what is that expression saying? What is that expression saying? It is not the case there exists at least one thing in this entire universe such that X is an element of S. Don't you think all the set that meets this requirement is an empty set? Okay? So I understand this is a very long and kind of scenic route of defining what an empty set is, but I want to relate something that you already understand to a new symbol that we're introducing today. So that helps to build more pathways between concepts in your mind. Yep.
It's only saying though that there is not one thing that's X.
It is
Does
saying
leave
that.
open the implication that Y could be an S? Does that leave
No, but X is a variable. Okay, in order to evaluate this expression here, we have to bind X to everything in existence, and then evaluate X is in S. Okay, so X is just a variable. It's the name of a variable that binds to actual things in the entire universe. But it can only bind to one thing at a time, right? So bind to one thing and say, are you in S? No. Next thing, are you in S? No, and so on and so forth. Are we okay with this or not?
I think so.
Okay, all right. So if we want to define intersection and union, this is how we define intersection, and this is how we define union. And you can see how union as a symbol has some resemblance to conjunction as a symbol. And you can also see how union as a symbol has a relationship with how we define disjunction as a symbol, because they are related in this kind of strange way. So we'll pick one, we'll pick the first one, and we'll talk about it just a little bit. Okay, so let's take a look at this one. So the first one says, for the entire universe, okay, for everything in the entire universe, X is in the intersection of A and B if and only if X is in A and X is in B. Okay? Now, this is if and only if, right? What if you pick up something and we say, oh, it's not in A intersecting with B? What do we know for sure? This expression is false. Okay? Which leaves us three possibilities. X is in A, but not in B. X is in B, but not in A. x is not in is in neither A or B. So those are the three possibilities if x is not in A intersecting with B. Is that okay? Now, you can also do it the other way around. You can say, pick something out of the entire universe, okay? And you check this part first. And you say, oh, it is in A and it is also in B. That means x has to be in the intersection of A and B, because that is how intersection is defined. Is that okay? So I'm really just redefining things that we have already defined, and some of you intuitively already understand, but this time we're using quantifiers just so that we kind of get some exercise of using quantifiers. Cartesian products. Okay, so this is the how we define Cartesian product using quantifiers. You can see this is kind of nested a little bit, okay, because the outermost portion of the quantifier says, okay, pick something in A. We're binding x to something in the set A. So by the time we get to the second quantifier, which is nested inside the first one, x is already known to be something in A. So now we say, okay, pick something in B, and we will bind it to variable y. Is that okay? So by the time we get to this part of the expression, let me just click it. So by the time we get to this part of the expression, we have already picked out something in A that we bind to variable x, and we have already picked out something in B that we bind to variable y. So this part is saying xy is in A Cartesian product with B. Is that okay? So this is basically forcing stuff in A times B. But can A times B, Cartesian product with B, contain something in addition to two tuples where the first item comes from A and the second item comes from B? That becomes the other question. So that's why we have this conjunction here. So the conjunction is actually on the outside of the quantifiers. In other words, this conjunction is treating this entire thing as its left-hand side, and is also treating this entire thing as its right-hand side. Now we already know what the left-hand side is saying. Okay, it's basically saying, for all the two tuples, okay, where the first item comes from x and the second item comes from y, those two tuples have to be in the Cartesian product of A and B. But then it leaves open the question of, well, can the Cartesian product contain something else? Okay, something that is not a two-tuple, for instance. So the second part is giving you that restriction. So the second part is saying, okay, let's look at everything in the Cartesian product of A and B. So each element of A and B, each item in the Cartesian product of AB are two tuples, x, y. So we look at those and we say x, the first item, has to be found in A, and then the second item, y, has to be found in B. So it's a restriction to make sure that it goes in both ways. So we are limiting what can a Cartesian product contain as elements. Is that okay so far? Okay. And then section 8 talks about subset of. Okay. So we take a look at the first one. A is called a subset of B. Remember, with a bar, it is just subset. Without a bar, it is called the proper subset, a proper subset of. So A is a subset of B if and only if, for every element in A, the element is also found in B. I think we saw that earlier, right? So proper subset of, A is a proper subset of B. We're talking about the second expression now. If and only if, okay, first one is A has to be a subset of B first, and there exists at least one thing in this entire universe such that that thing is in B but not in A. So you can see how we are re-expressing concepts that we have already talked about. Just this time we are using quantifiers to help clarify. Okay, what are we talking about? At least one for everything, or what? Yep. Go ahead.
This is kind of about the Cartesian one. So the left side of the conjunction, the for all x.
Mm-hmm.
So if X was not in the set of A,
Mm-hmm.
that statement is still true.
It won't. Okay. If this part of the quantifier limits that we're only considering X that is in A. Remember, this is a shorthand of saying for everything, for every X in the entire universe, X in A implies the following. Yeah, so the highlighted portion is already doing the filtering. It's saying, don't look at anything else, okay? We only want to look at things in A. And that limits our consideration for everything after that is only saying that, okay, we know for sure that we have picked out something in A and we bind it to a variable X. Are we still doing okay so far with quantifiers? Okay, all right. So if that is the case, I am going to release the first homework assignment. Yeah, so I'm going to release a set theory. I will do it after the class. Okay, so right now it has a due date that is in the past. So unless you're a Time Lord, okay, look at my T-shirt. So unless you're a Time Lord, you cannot get the homework assignment done and get credit. So I'm going to have to change the due date, and then you guys can start to work on it. So I'll give you a week to do this. So the due date is going to be next Wednesday before the lecture, so that I can talk about the solution during the lecture. For those of you who have taken assembly language from me, this one does not allow multiple attempts, so you don't want to keep poking it. So yeah, you can open it. You can let it stay open until the due date, but don't submit unless you are sure that you're ready to submit, because it does not allow multiple submissions, okay? Because the idea is I want you guys to really think it through before you turn it in. Yes?
Is there an access code for it?
No, there won't be any access code. I just have to change the due date and you can get to it. In fact, I'm just going to do it now. I think somebody should invent a drone technology that can track down noise, sources of noise. And we'll have those drones to fly around this campus and just kind of chase down cars with those coffee can tailpipe. I think by itself, that's a really great engineering / STEM project, because how do you know the direction of a source of sound, right? So that's the first thing you have to resolve. Let alone,
I thought they already had those for like search and rescue applications.
I would not be surprised. So they probably use triangulation and also phase change, phase difference between two microphones and stuff like that. All right, so I just have to change the due date to let's see, today is the 29th, so it's due on the 5th of February and due at the start time of this class, which is it's still 12 p.m. Okay, so that works. I'll take this away and then make this the same as the other one. And save. So now you should have access to it. So remember, you can open it anytime before the due date and you can leave it open until the due date. But do not submit unless you're 100% sure that you don't want to change your answer. Yep. I cannot remember. To tell you the truth, I cannot remember. I can do a preview and you can. Yeah, so it's mostly multiple choice, but there's one that is an open-ended question here. So some of the questions I have to grade manually, and some others, it's just multiple choice. So it's a mixture of question types.
I got a glimpse of that question number 2, asking that we provide the correct notations.
Mm-hmm.
Okay, so we're not going to end up having to use those arrows for and or anything in the answer, because I actually don't know how you.
Well,
would go
this
about
one, define a membership arrangement of A and B to satisfy the constraints. In other words, I want you to tell me what is in A and what is in B. So you say A is blah, 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 and B is blah, blah, blah.
Okay.
Okay? But you have to use the right notations. Okay? So remember what parentheses mean, remember what curly braces mean, remember what the bars mean, because if someone is mixing up those enclosing symbols, points will be deducted. Yep.
Since we have a graded assignment, does that mean we can't have an ungraded assignment?
I can still give you ungraded assignments based on what we get through today. Yep. So I can, if I remember, I'll do it. Okay. If I don't remember, you can nudge me. Yep. All right. Well, we still got 12 minutes left. Okay. So we'll go ahead and continue. So the next topic after set theory is the topic of functions. Okay. So functions. Okay. Most of you have taken probably pre-calc or at least one of the calculus classes, right? So you know what a function is, okay? Sine is a function, cosine is a function, log is a function, blah, 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 okay? But in this class, we are not talking about functions like that, okay? Because those functions are continuous functions. In other words, when you look at, let's say we want to take the sine of something, okay? What can I take the sine of? Are they limited to just integers? I can take the sine of 1, I can take the sine of 2. No, you can take the sine of half of pi, right? So the range of values of what you can supply to the function as an argument is continuous in the case of sine, cosine, log to the power of, that sort of stuff. In this class, it is all discrete, which means for the most part we're dealing with integers, but not always just integers. Okay. All right. So the first idea is, well, we're going back to tuples. So a tuple can be seen as an array, you can see it as a list, but the idea is if you have a two tuple, it means you have two items. Okay? And then between the two items, the ordering is important. So 1, 2 as a two tuple is considered different from 2, 1 as a two tuple. They are considered entirely different. Okay? A tuple is not a set, which means you can have a two tuple and the first item is 1 and the second item is 1, 2. That is actually perfectly okay. Is that okay? So remember, a tuple is more like an array. So that's basically what the first section is talking about. It's just a reminder or a review of what the tuple is. So now we look at the function, okay? And we look at this really simple definition of a function. F of x is 2x, okay? And we already know, well, if f of x is 2x, then f of 2 is 4, f of 3 is 6, f of 1 is 2, f of 0 is 0, f of negative 1 is negative 2, and so on. Yes? Okay? But we don't want to define functions this way. Okay? In this class, we want to define functions as a set of two tuples. The first concept, before we even talk about a Cartesian product or the two tuple, is we want to be able to describe a function, and the first thing we need to do is to identify the domain and the codomain. Now, if you have taken some math classes and your math professor says, okay, here's the domain, and we map things in the domain to a range, it's okay. So the concept of a range or the word range in the discussion of a function has exactly the same meaning as what we use a codomain to represent in this class. So if you have already understood what a range is in your other classes, you just say, okay, Tech calls a range a codomain in this class. If you have not exposed to the concept of a range, hey, it's not a problem. So the symbol, if I want to define a function f, where x as a set is the domain, which is where the value, which is the from, okay, and is mapping values in the set x to values in the set y, that means y is the codomain. And this is the symbol to illustrate f is a function, x is the domain, and y is the codomain. That's all it's saying, okay? It doesn't say exactly how things are mapped. It is only identifying that we are mapping things from x to y. Is that okay? All right? So that's just a symbol. And in the function that we have earlier talked about, which is f of x is 2x, now that can be defined over just any, you can define it over real numbers, you can define it over natural numbers, you can define it over all integers. But since in this class we want to deal with discrete values, so we'll limit it to integers. So remember, this kind of funny looking z symbol is representing the set of all integers. So in this case, what we are seeing here in the highlighted portion is saying we're defining f as a function, we're using integers as the domain, but we are also using integers as the codomain. We are mapping integers to integers. Is that okay? Are we good? All right. So now we look at what is in that set. Remember, we want to look at a function as a set. So in this case, this is going to be what is inside the set, or just an example of what some of the elements may look like in that set. 0 is mapped to 0, 1 is mapped to 2, 2 is mapped to 4, 3 is mapped to 6, and so on. So let's take a little pause right here. Are there any questions? Are there any questions about this new way of looking at functions? A function is a set of two tuples where the first item comes from the domain, then the second item comes from the codomain. So each element in that set is telling us how a specific value from the domain maps to a particular thing in the codomain. That's the bottom line. Are we good with this concept? A slightly new way of looking at functions. Yes?
So 0 maps to 0, 1 maps to 2.
Yep. Yep. So that's basically what it's saying. 0 maps to 0, 1 maps to 2, 2 maps to 4, 3 maps to 6, and so on. Okay? But then somebody's going to say, what about 5? 5 maps to 10, not a problem. But what maps to 5? Nothing. Nothing. Because 5 divided by 2 is 2.5. But 2.5 is not in the domain. The domain is limiting to just integers. And 2.5 is a rational number, which is a superset of integers. And we are not considering rational numbers. Is that okay? Yep.
If the domain is integers, does that mean the function is a infinitely large set?
Yes, so you're correct. Well, not necessarily, okay? Not necessarily, but in this case it is. So because in this case, the actual definition of the function is to map every single integer to twice of its value. Let me correct myself, okay? What you said was actually true. Because the domain itself is infinitely large, the function is also a set that is infinitely large. So we'll talk about what qualifies as a function, and one of the qualifying condition of a function says the number of elements of your domain would be the number of elements in the function as a set. Now, because we're considering the set of all integers as our domain, and that is infinitely large, so that means the cardinality of the function itself as a set has to match, and that is also infinitely large. So I stand corrected, you were right about that. All right, we still got about 4 minutes, so we'll kind of move on a little bit. All right, so, but I cannot enumerate all the items, listing individual items out. So I'm going to use this notation here and say that f as a function, but seen as a set of two tuples, can be described like this. Every two tuple in f would have two values. And each value, the first item of the value has to be, I should say the other way around, the second item of the two tuple has to be twice the value of the first item of the two tuple. And then the first item of the two tuple has to be coming from the set of integers. But in earlier lectures, like even today, and also the one before today, we talk about how this is really just a fancy way of writing this. So basically, they're saying the same thing. If you, well, actually, they're not exactly the same thing, but these two are equivalent. If you choose x in the integer set and you choose y from the set of all integers, so now you can pick anything, right? You can say x is 1 and z is 3, y is 3, okay? But now you have to pass this test first. So this test is saying if y is exactly 2 of x, then xy has to be in the set F. Okay? But because this is if and only if, so that means if you pick something from x, you pick something from y, and just by luck, okay, you find xy to be a 2-tuple in F. What is that telling you? The arrow goes the other way, so it tells you that y has to be 2x. Is that okay? All right. And then section 3.1 talks about the qualifying conditions of what makes a function a function. So I want you guys to read this over the well, it's not a long weekend, but there are 5 days before we meet again. So I want you to read this portion, okay? Because eventually you will read something like this, okay? And if you read the note step by step and actually put time into understanding the concepts, you will understand what this actually means, okay? But at first glance, that is kind of difficult to understand, okay? But you will be able to understand it if you just kind of follow the steps and remember the definitions of all the symbols that we have encountered up to this point. Okay? So I'll see you guys next Monday. Have a nice weekend. Yep. So let me turn off the recorder first.